let's consider a pretty standard hypothesis test. Suppose we have the null hypothesis on a population mean equaling some value, mu sub 0, versus the alternative hypothesis that this is not the case, that the true population mean is not mu 0. So we can take a sample to get a test statistic. Get a test statistic, and we should know by now that x bar, the sample mean, is the appropriate test statistic. And if we're going to run a hypothesis test, we want to fix the probability of type 1 error. We fix the probability of type 1 error in advance. Fix the probability of type 1 error. Type 1 error, as we've seen in the previous video, is alpha, probability that you make the wrong decision when the null hypothesis is true. The probability that you reject the null hypothesis when it is true, given it is true. Given that it is true, and you usually choose some small value here because you do not want to be rejecting the null hypothesis if it's true, right? And so you want to be very confident that you are making the correct decision when you are rejecting the null hypothesis, all right? We do not want to reject the null hypothesis lightly. Common values are things like alpha equaling 5% or lower, all right? Sometimes you'll see a 10% alpha, but usually 5% or lower. 1% is common as well. It's somewhat arbitrary though, so that's a little weird. But you'll see in examples we're usually given an acceptable value for type 1 error. All right. So what do we have to work with? Well, if we assume, remember, this is given h naught is true, assuming the null hypothesis is true. Assuming this is true, right? That is, that the population mean is actually whatever mu 0 is, then we have a standard normal random variable when we look at x bar minus that mean, mu 0, divided by sigma over the square root of n under the central limit theorem. This is a standard normal. And so we can calculate the probability then of getting different values for this z. We can calculate the probability of getting different z values. And we can do so that the probability is tied into the type 1 error alpha. Right? The probability that my z value is between negative z of alpha over 2 and positive z of alpha over 2 is 1 minus alpha. X bar minus mu 0 over sigma over the square root of n is 1 minus alpha, right? So again, let's take some numbers. Let's say alpha is 5%, right? Then there is a 95% probability that the statistic I get, x bar, yields a z value after this transformation between these two endpoints, negative z of alpha over 2 and z of alpha over 2. There's a 95% probability. There is a 5% probability that we are outside these limits, okay? And those are the cases where we would reject the null hypothesis. We reject the null hypothesis if we get a z value that is bigger than the right endpoint or smaller than the left endpoint. Negative z of alpha over 2. This is a two-sided test. This is a two-sided test. This is a two-sided test. We've also can look at one-sided tests. So how does this change in a one-sided test? In a one-sided test, well, first of all, your hypotheses really decide what type of test you have. Okay, so when you're looking at a one-sided test, you might have the null hypothesis that mu is equal to mu sub 0, but in a one-sided test, the alternative is, well, one direction. That is, maybe mu is greater than mu is 0, right? Versus the two-sided test, not equal to could be larger or smaller. So in this case, it would just be larger. And in this case, under the null hypothesis, right, again, assuming the null hypothesis is true, the probability that x bar minus mu over sigma times root n is greater than z sub alpha, related to something you might have looked at when you're doing a one-sided confidence interval, right? This is by definition alpha percent, alpha. And so we, in a one-sided test, we reject the null hypothesis if we are bigger than this value. Is bigger than z of alpha in a one-sided test. All right. Similar in terms of mechanics and computation, this hypothesis testing stuff is similar to doing some confidence intervals. There's a lot of similarities here, but we're not actually calculating a confidence interval. We are just running a test, and we will either give a conclusion that is reject the null hypothesis or not to reject the null hypothesis. Let's dive into an example and see what this looks like with some actual numbers. A random sample of 100 deaths in the U.S. during the past year showed an average lifespan of 71.8. Assuming a population standard deviation of 8.9 years, does this indicate the mean lifespan today is greater than 70 years? Use a 0.05 significance level. All right, so there we go. We know our significance level alpha is 5%. All right. So in order to do the hypothesis test, we have to start with, well, the hypotheses. What should the null hypothesis be here, and what should the alternative be here? Well, the assumption, kind of the underlying assumption, right, is sort of that the going rate is that the mean lifespan is 70 years, right? You have an average lifespan of 71.8. That's the sample average. Does this indicate the mean lifespan today is greater than 70 years? Is greater than 70 years? This sentence actually kind of outlines what the alternative hypothesis should be, right? And maybe we could start with there, saying, well, clearly the alternative hypothesis that we're sort of testing against is the mean lifespan greater than 70 years? Well, then what is the alternative, or what's the null hypothesis? Remember, the null hypothesis needs to be clear and definite. And so this should be that we are assuming the mean lifespan is 70 years, right? Let's not make the mistake and think of complement events. We don't need to do anything like this. This should be clear and definite. Mu equals 70. All right. This is a one-sided test. Greater than 70 years. This is a one-sided test. So what are we going to do? Well, we need to compute our z value, and we will use that and reject the null hypothesis if z, which is x bar minus mu over sigma divided by the square root of n, is greater than, well, let's just see here. It would be greater than z sub alpha. In this case, it's a 5% significance level, z of 0.05. Z of 0.05. And so we can go to the normal table and look at where z of 0.05 is. Should have some normal table familiarity now. 1.645 is the associated z value that we'll look at. All right. So what is our test statistic say? Well, we have a sample mean of 71.8. So x bar is 71.8. The assumed population mean is 70. Is 70. divided by sigma, population standard deviation of 8.9, over the square root of n, and this was a sample size of 100. And so we run that number through a calculator. And this is rounded off about 2.02. 2.02. 2.02 is bigger than 1.645. Bigger than 1.645, which is our cutoff value based on our level of significance. So we reject the null hypothesis. We reject the null hypothesis and claim that the population mean is now greater than 70. We claim that the average lifespan is greater than 70 at a significance level of 5%. We reject H naught. Our conclusion is that we would reject. We reject H naught and claim the population mean is greater than 70 at a significance level of 5%. Okay? We're pretty confident, right? It is so unlikely to get a z-value of 2.02. It is so unlikely to get that statistic, assuming if the mean was actually 70, if the population mean was actually 70, there is a less than 5% chance that we would get this 2.02. It's still possible. It's in the realm of possibility, but it's very unlikely. And so we can confidently reject the null hypothesis and accept the alternative. And accept the alternative. All right? And that is our one-sided hypothesis test. Okay? I want to offer an alternative solution to this. And you might be saying, alternative solution? I mean, this is the hypothesis test. Well, yeah, there are alternative ways to sort of reject your null hypothesis. And that is using what's called a p-value. Using a p-value. Okay? So what is a p-value? A p-value is the probability of getting a more extreme test statistic of getting a more extreme test statistic than what you observed. All of this, of course, is assuming the null hypothesis. Assuming the null hypothesis is true. P-value. Probability of getting a more extreme test statistic than what we observed. So in this case, we got a value of x bar of 71.8. So a more extreme test statistic should be in the favor of the alternative hypothesis. More extreme than 71.8 would be bigger than 71.8. In this case, x bar was 71.8, so more extreme is getting an x bar bigger than 71.8. It's getting an x bar bigger than 71.8. Okay? And what could we use this probability for? What is the point in doing this? Well, let's just figure out what this p-value is first, right? So the p-value here is the probability that we get x bar greater than 71.8 given the null hypothesis is true. Well, if the null hypothesis is true, right, then this is, we can find the z-value here. This is the probability that z is greater than 71.8 minus 70 over sigma divided by the square root of n. Right? We just switch this up to a greater than symbol compared to before. And so then this is just the probability that z is greater than 2.02. Probability that z is greater than 2.02. And then so we can go look at the normal table. What is that probability? The normal table gives us values less than 2.02. That's 97.83%. So greater than would be the complement, 1 minus of that. and this is 0.0217. That is 2.17% chance. That's our p-value, all right? There is a 2.17% chance of getting a test statistic more extreme than the one we observed. More extreme than the one we observed. What do is we compare the p-value to the predetermined level of significance. Compare p-value to your level of significance alpha. If p is less than alpha, we reject the null hypothesis. If p is less than alpha, we reject the null hypothesis. Okay? And in this case, alpha was 5%. So since 2.17% is less than alpha, 5%, our significance level, then we would still reject the null hypothesis. You would still reject the null hypothesis. Okay? So the p-value is the probability of getting a more extreme test statistic. More extreme test statistic is saying that getting anything further from this compared to the assumed population mean is so unlikely. It's so unlikely that we would reject null hypothesis. And remember, because these are continuous random variables, right? The probability that z is greater than 2.82 is the same thing that z is greater than or equal to. So more extreme is like this value and higher in some sense, right? More extreme could technically be including, because this would not change the probability if these were greater than or equal to's, right? That would not change the probability. And it's so unlikely to get anything in this realm that we would reject the null hypothesis, okay? This is a good point to pause and take a break. If you have any question on this first example on either using the p-value or just the traditional test versus significance here, post those in the discussion thread below, and we will have more examples maybe in a future video. We'll see you in the next video.